Okay, so we're going to talk about acids and bases, and we're going to talk very briefly about some properties of acids and bases today, and what the pH of a substance tells you about whether it is acidic or basic. So, like I said, there's two different definitions of an acid. Technically, there's three. And so we're going to focus on two of them. The first one is something that is called an Arrhenius acid, which is something that adds more hydrogen to water in an effort to form something called the H3O plus ion. Now, the H3O plus ion has a very special name. It's called the hydronium ion. And it's basically a water molecule with an additional hydrogen attached to it. So an Arrhenius acid is something that adds more hydrogen to water. As a result of adding more hydrogen to water, it creates the hydronium ion. And then there's the technically Bronsted-Lowry definition. It's something that donates a hydrogen to another substance. So the example of something donating hydrogen to another substance would be something like this. So here I have HCl and I have water, and then this H right here gets donated to the water to become H3O plus. So the Arrhenius definition of an acid and the Arrhenius definition of a base are very similar, however, they're subtly different. Okay. One is something that increases the concentration of H in water, and the other one is something that donates a hydrogen to another substance. So those are two very similar definitions that are getting at the same thing, whether or not a substance is acid or base. And all acids have these similar properties in them, or we can identify them. Acids will react to neutralize bases, is a property. So if you mix an acid and a base together in the appropriate amounts, you neutralize the base, and we'll talk about what that means in a second. And the acid itself also becomes neutralized. Acids, thank you. Acids will change the color of acid-base indicators. What that means is that we have a substance that we can put into a solution that will maybe start out as clear, and as you add acid to it, it will change color. Or the substance will start out as a color, and as you add acid to it, it will change into another color. So that's what acid-base indicators are. Acids tend to have a sour taste. Now, first of all, we never taste anything in the lab, but we do know that acids have a sour taste. There are some acids that are safe for us to consume, and they all tend to have a very similar taste, which is sour E. So think like citric acid in your oranges, lemons, and limes. Phosphoric acid in very, very small amounts tends to give some soda the taste that it has. So they acids have like I said, a sour taste. I don't want to be responsible for any of you testing that, so we're not going to. So when we do the lab in this class, please don't taste the acid. Okay. Acids produce hydrogen when reacted with active metals. So what does that mean? That means something like if I take hydrogen chloride, which is an acid, HCl, and I mix it with something like zinc, just zinc metal, I will produce zinc chloride and hydrogen gas. And we did a demo like that a long time ago. Like it feels like forever ago, but it was earlier this school year, where when we did that demo, what ended up happening is that we had produced a little bit of hydrogen gas. So I think I balanced that correctly. And then lastly, acids have pH values less than 7. And we're going to talk about pH in a little bit. But basically anything from a pH of 0 all the way to like 6.9 would be considered acidic. Okay. All right, next. So there are some common acids that you might find in your daily life. Things like sulfuric acid is the acid that's found in most batteries. Well, it's most car batteries. We don't see it a lot in the batteries that you put into your remote. I was trying to come up with something that you might put batteries in because everything has got a battery built into it right now. Back in the day, I used to be able to say things like, in your Discman. No. I know. So remote. I mean, I used to be able to say things like, in your gaming console controllers, but you now have rechargeable batteries in those too, right? Like
remotes. I can't recharge my remote.
That's true. We can't recharge the remote. So, and it's most annoying that whenever the battery dies in the remote, you can never find two batteries of the same kind. So you steal them from something else and put them in there, and then yeah, good times. All right, nitric acid is used in the making of fertilizer. It's also a pretty caustic acid, so we don't use it very often. Hydrochloric acid is commonly found in stomach acid. It's also found in some cleaners. Citric acid is found in your lemons, limes, and other citrus fruits. Phosphoric acids are found in tangy and or sour sodas, like I said before, and acetic acid tends to be found in vinegar. So those are some common acids. Those are not all of the acids. There's lots of acids out there, but those are some common ones. So now we're going to transition and talk about bases. Bases are substances that release hydroxide in water. So, or increase the concentration of OH in water. So, an Arrhenius base is something that increases the concentration of hydroxide in water. So one of the things that we should kind of think about is that water is oftentimes written like this because that's a true statement. But in reality, when we draw water, we oftentimes draw water like this because that's the structure of water, right? So water can also be written like this. It's the same thing. So because it's the same thing, when we talk about releasing or increasing the concentration of hydroxide in water, we're really talking about a substance that when it dissolves in water, it makes more of this. Okay. And so then that's the Arrhenius definition. And then the Bronsted-Lowry definition is a substance that accepts a hydrogen from another substance. So an example of that would be, if we go back to the HCl and the H2O, right? In this instance here, we would end up with Cl minus 1 and H3O plus. So this acts like a base because it accepted a hydrogen. And this acts like an acid because it donated a hydrogen. So the Arrhenius definition of acids and the Bronsted-Lowry definition of acids are very, very similar, but the Arrhenius definition of bases and the Bronsted-Lowry definition of bases are a little different. So in this case here, the water is acting like a base because it accepted a hydrogen to become H3O plus. Okay. A common example of a base is sodium hydroxide. If we take sodium hydroxide as a solid and we put it into water, we get aqueous sodium and we get aqueous hydroxide. And by simply adding something with hydroxide to water, we're adding more hydroxide. So we're increasing the amount of hydroxide in solution, thus satisfying the definition of an Arrhenius base. What? Oh, it is fancy. Yeah, it is kind of fancy. Now, some properties of bases. The properties of bases are not as many as the properties of acids, but they are still important. So bases tend to neutralize acids, and that's something we're going to focus on tomorrow in class. But what I mean is that if I have an acid and I add base to it, I can make the acid become neutral if I add them in the appropriate amounts. Bases also change the color of acid-base indicator, as something that we talked about before, and bases tend to feel slippery when touched. So an example, a very common example of a base that you would have around the house is soap, maybe even bleach. Because if you get either of those things on your fingers and you feel like this here and you go to try to rinse them off, it feels slippery. And so like those are common examples of bases. And then bases tend to have a pH value greater than 7. So anything from like 7.1 all the way up to 14 would be considered a base. And just like we talked about with acids, what are some common bases? One of the common bases is sodium hydroxide. We use that to make soap. Sodium bicarbonate, which is the active ingredient in baking soda that you might have in your refrigerator or at home in your baking cabinet. Sodium carbonate is found in antacids. So when you've got an upset tummy, you take a Tums, which is essentially a lot of sodium carbonate, and it neutralizes the acid in the stomach. And ammonia, which is a cleaning agent. It's the most common place you would find ammonia, NH3, in your house is probably Windex or something along those lines to clean the windows. And it smells awful. Yes, ammonia smells awful. And so
like bleach, but it smells like dingy. Like it smells like dirty bleach in my opinion. Like it smells like a chemical, but it also smells like really like if it was like a spoiled chemical.
It's very pungent and it definitely smells awful. So a lot of times we find ammonia in, like I said, in Windex, but it is a great cleaner. It just smells bad. So speaking of pH, we've talked about it a couple of times. Let's talk about what it actually is. pH is a scale that's used to measure the acidity or basicity, which is another word. The more sciencey term would be alkaline. Like your alkaline battery. You ever heard of that? Maybe, perhaps. So pH scale, it measures the acidity or the alkalinity of a solution. It's logarithmic, which means it's based on powers of 10. And acids have a pH less than 7, bases have a pH greater than 7, and anything neutral is considered to have a pH of 7 itself. So another thing that we want to think about, though, is that acids have a lot of H3O plus, right? And bases, Arrhenius bases, tend to have a lot of OH minus. Oops. Okay. So a lot of times when I think about what is an acid, I think about the amount of H3O plus that it has. And sometimes when I think about a base, I think about the amount of OH minus that it has. And then anything that's neutral can be considered a pH of 7. And the most common neutral substance that we ever deal with is pure water. So the water that comes out of the tap is going to be slightly acidic or basic depending on what is in your pipes. But pure water itself, ideally deionized water, the water that we tend to use in the lab, has a pH that is equal to 7. So what's the pH scale? Here's a pH scale with some common things that you might come across. Things that are acidic, 0 to 6, are things like batteries and stomach acid and lemon and soda and tomatoes and coffee and milk, and things that are basic are things that like your blood or your egg whites or stomach acid, or I'm sorry, stomach tablets. Call that an antacid, because I don't know what happened there. Wow, spelling is hard today. So hard. Antacid. I think I spelled that wrong, but I'm giving up. Ammonia solution, soap, bleach, and drain cleaner. Now, the larger the number for the pH or the smaller the number for the pH, it is considered to be the more basic or acidic that it is. So things that are closer to neutral are considered to be less caustic or less dangerous to the human body. So, like we've discussed, substances with a pH less than 7 are considered acidic, and the closer the pH gets to 0, the higher the concentration of H3O plus gets, the more acidic the substance gets. Now, I'd like to point out that Hollywood likes to make you think that, like, the vat of acid, right? And then you throw somebody's hand in there and they stick their hand in the vat of acid and they pull their hand out and it turns into skeleton hand. You know what I'm talking about? You ever seen that in the movies? That's not really how it works. Like, it takes a lot more time than just like dipping your hand in there and pulling it out. Would you get a burn? Absolutely. Would it be awful? Absolutely. Would you be in a lot of pain? Absolutely. But would you stick it in for a few seconds and pull it out and be skeleton hand? Hard no. It takes a lot more time than that. But Hollywood's got to speed some things up, so that's what they do. Now, so the pH scale is based on what I said was something that was a logarithmic. So in the case of like something that has a hydrogen ion concentration of like, I don't know, 1 times 10 to the minus 4, would have an OH concentration of 1 times 10 to the minus 8 because it has to basically add up to 1. So something like tomato juice. So as you get more and more closer to a H3O plus concentration of 1, the more acidic the substance is. We've said that battery acid is sulfuric acid, and sulfuric acid, if not dealt with appropriately, can cause a pretty severe chemical burn. Whereas pure water has a pH of 7 and has a hydrogen ion concentration of 1 times 10 to the minus 7. So it's really relatively safe, and I can't think of anybody that I can think of that's allergic to water. So there's that. And then again, bases are substances with a pH greater than 7. And the closer you get to the pH of 7, the higher the concentration of OH minus is, the more basic a substance is, the more caustic it is, the more dangerous it can be. So again, here's our H3O plus concentration. Here's our OH minus concentration. And they are basically opposite of each other. So the bigger the OH minus concentration, the smaller the H plus concentration when we're talking about acids and bases in terms of pH. And if they're equal, then they're neutral. Any questions about this? All right, so there are some calculations that are associated with the pH of acids and bases. We're not going to jump into those this year. So you do have homework this evening, which is the first worksheet in the packet. I believe it's a one-sider. The question on the question on the bottom is a challenge problem that we'd like you to try. You technically don't need to know anything about acids or bases to answer that question, but it is acid and base related. So you have some time to work on that as part of your homework. Ready, set, do some work.